All right, let's get started. Today I'm going to tell you about proving the correctness of C programs with the verified software toolchain. C programming? Really? So here's a claim that some guy made. Purely functional programming is the shortest path to writing and proving a program. And what program did he prove? A C compiler. Now, it's not worth proving the correctness of your compiler if you're going to feed buggy programs into it. And it's not worth proving the correctness of your programs if you're going to feed it to a buggy compiler. So anyway, purely functional programming is the shortest path to writing and proving a program for most software. For software that can tolerate a slight performance penalty, and you look at all the software written in Perl and JavaScript and Python, and they can all tolerate a slight performance penalty, and that's fine. For software that can tolerate the latency penalties and sort of the need for a runtime system that is implied by having a garbage collector. And again, look at all the programming languages that are in use nowadays that can tolerate having a garbage collector. Or for programs that don't need a runtime system. Because, what's the runtime system written in, and you've got to prove it correct. So most software should be written as purely functional programs and proved correct in the beautiful proof theory of functional programming. But there is a little bit of software, like only a few millions of lines of code, that may need to be written in a low-level, industry-compatible imperative language, and that you might want to interface to the rest of your proved correct software. So, to prove a program respects a functional specification, you typically use a program logic. Now, what Zhang Xiao was showing you the last few days is a way to prove C programs correct by refinement. It's not quite a program logic, so that's why I say typically. And the program logic for Galena is Coq itself. And there's a nice integration there. But the program logic for imperative languages, languages where you can mutate shared state, is typically some variant of Hoare logic. So you remember Hoare logic. You have some command that changes things, and you have a precondition and you have a postcondition, and you write down the Hoare triple like this with the pre and post conditions in braces. And what it means is, this judgment, if the state satisfies the precondition, then it's safe to run the command. The command will not exhibit undefined behavior. And the state afterwards will satisfy the postcondition. So there's an example of a Hoare logic judgment. If x equals 5 and y greater than 0, and you execute x gets x plus y, then x is greater than 5 and y is greater than 0. Now, this is not the most specific judgment you can make about this program. It doesn't quite capture that the amount that x is increased by is equal to y, so you could make more refined specifications and prove that the programs satisfy those too. All right, so here's why we can't just use Hoare logic. Well, traditional Hoare logic, and by traditional, Hoare logic was invented around 1969. So programming languages in 1969 didn't have pointers. And, so Hoare logic in the 20th century didn't deal well with pointer data structures and sort of the aliasing and anti-aliasing facts you want to remember about your pointer data structures. And that includes arrays and array slices they didn't deal very well with. Or function pointers. Think about your C programs that have void star function pointers all over the place. And it's actually correct, although you can't tell it from the C type system because of all the casts. But people roll their own object protocols in C, and the function pointers actually work out somehow. And Hoare logic in the traditional version is not really capable of proving those things. What about data abstraction? What we learned from type theory in the late 20th century is that the way you represent data abstraction is by existential quantification over predicates, or over types, as it was in type theory. And, the logics used in Hoare logic don't necessarily deal with that very well. And then, of course, you write Hoare Logic proofs on paper, or by the end of the 20th century, you would write them in LaTeX. But who's going to check them? You know, proofs of mathematical theorems can be concise, especially if they're giving you mathematical insight. But proofs about software, well, software isn't even concise, so how could the proofs about it be concise? So in the 21st century, we use descendants of Hoare logic to prove things about imperative programs. The way we deal with pointer data structures and aliasing and anti-aliasing facts is, many of us, by using separation logic, invented by John Reynolds and Peter O'Hearn and others around 2001. The way we deal with function pointers and their interaction with mutation, and that's a really weird interaction, and with data abstraction, is often with impredicative logics that have step-index models. And that technology, you know, that logical technology also dates from around 2001. And when we prove things about software, we really must do it in machine-checked proof assistance or other kinds of machine-checked theorem provers. When we prove things about algorithms, algorithms are mathematical objects that are elegant. We could do that plausibly on paper. But programs, software, a proof about a program, even if it were the right theorem about the right program, if it was written down on paper, then as the program gets maintained, what keeps the proof maintained along with it? So we need machine checking. And fortunately, we have good proof assistants these days to do that. So here's separation logic. This is a paper that John Reynolds published in LIX 2002. LIX is actually good for something once in a while. And, you know, I'll read you a little bit of the abstract. In joint work with Peter O'Hearn and others, based on early ideas of Burstall, we have developed an extension of Hoare logic that permits reasoning about low-level imperative programs that use shared mutable data structure. The simple imperative programming language is extended with commands, not expressions, for accessing and modifying shared structures, and for explicit allocation and deallocation of storage. Assertions are extended by introducing a separating conjunction that asserts that its subformulas hold for disjoint parts of the heap and a closely related separating implication. Coupled with the inductive definition of predicates on abstract data structures, this extension permits the concise and flexible description of structures with controlled sharing. Okay, so that's separation logic. And the star there is that separating conjunction operator. So when we write a precondition in a separation logic judgment, it doesn't describe the whole state. It describes some particular subset of your heap with a particular footprint, not necessarily the whole heap. By heap, that's theory E's for memory. Okay. You could run this command in an actual memory, not just a particular subset of the memory described by the precondition. But what the judgment says is that the command accesses only the data mentioned in the precondition and modifies only the data mentioned in the precondition and leaves you with only what's in the postcondition. Or if the command mallocs, then it may add some data to what's in the precondition and have a bigger postcondition, and so on. And the separating conjunction means that the subheap characterized by the predicate P is disjoint from the subheap characterized by the predicate Q, and together they join to make the whole subheap characterized by the precondition pre. Okay, so here's an example. I have a C command, x.data gets 3, and on the left I have this picture, a linked list. X points to, you know, a struct with a 1 and another pointer, and the other pointer points to a struct with a 2 and another pointer. And I have a local variable y that happens to point to that second struct. And the star says that the portion of memory characterized by x maps to 1, y is disjoint from the portion of memory characterized by x, y maps to 2, z. So from this we know y is not equal to x. And so even if there were a 1 here, and a 1 there, obviously, we would still know that x is not aliased to y. And that is useful because we want to mutate x. We want to store into x and still know that y, the contents of what y points to, has not changed. And that's the main point of the anti-aliasing encoded in the separating conjunction. Okay, so let's implement that for a real programming language, C, and let's prove the program logic sound with respect to a real operational semantics for C. And so what you get that way is the verified software toolchain. And it layers the proofs as follows. The C compiler is proved correct. So whatever the behavior of the program that runs in the operational semantics of CompCert C, and that's formalized in Coq, well, this machine language program will have the same observable behavior. That's the CompCert compiler correctness theorem. And the program logic is sound. That means whatever behavior you use the separation logic to characterize, whatever specification your program satisfies as you prove in a derivation in the Verifiable C program logic, this source code, when it runs in its source level operational semantics, will actually have that behavior and only that behavior. And then finally, the user proves in Coq using the proof rules and proof automation of Verifiable C that the source program has some behavior. And you can compose all those proofs together and get a proof about the behavior of your machine language program. So Verifiable C hooks up to Coq, to CompCert in some way. And the way it hooks up is like this. You have your program. Actually, it's my program. And the front end of CompCert parses it. Now, my program.c is in ASCII. That doesn't really have a semantics. But the front-end parser parses it into the abstract syntax trees for CompCert C, and that does have a semantics. Then we use 2 more of the front-end phases of CompCert to translate, compile this language into that language with correctness proof. C-Lite. C-Lite is a subset of C. Unlike the rest of these intermediate languages, a C-Lite program really is a legal C program. It's just a C program that doesn't have side effects inside expressions, basically. And in which, you mark which local variables are addressable local variables, things that, you can point to, and which local variables behave more like variables that you can't point to. All right, so that's C-Lite. So we ask the very front end of CompCert to parse the C program into an abstract syntax tree. And then in Coq, we apply the Verifiable C program logic to that abstract syntax tree. And then we can use the rest of CompCert to compile the C-Lite abstract syntax tree all the way down to assembly language. So I regard this as really the source program. And that means this stuff doesn't even need to be correct. Because what I've proved is that that C-Lite program has a specified behavior in the C-Lite operational semantics. Didn't matter so much how you got it. Now, it does matter a little bit how you got it, because the programmer would still like to read the program and understand it and learn things about, for example, its asymptotic efficiency that we don't prove things about in Verifiable C. So it matters a little bit that this is correct, and I'm glad that it is correct, but it's not really part of the trusted part of the system. Okay, so here's a program. Let's reverse a list in place. Where have you seen this before? Where have you seen this before? Let me ask, why have you seen this before? So let me go back to Reynolds' original paper. And in the first page of the paper, in half a column, he lays out the list reverse program and the loop invariant and the inductive definition of the list predicate. So Adam Chapala showed you all of this, right? Reynolds did it in 3 column inches. To be a member of the separation logic club, you have to do list reverse first. So I will do list reverse first. Here's my program. We take as an argument the list P, and we're going to return the reversal of that list, and in the process destroying P. So let's set W to null. Let's set V to P. So, all right, now, while V is not null, indeed, V is not null. That's a con cell there. So let's do this. Let's set T gets V arrow tail, and then V arrow tail gets W. So now we have this picture. And then we're going to set W gets V, and V gets T. So we'll have this picture. And now we're at the end of the loop body. V is still not null, so we'll do another iteration of the loop, and we will have this picture. And V is still not null, so we'll do another iteration of the loop and have this picture. All right. And now V is still not null, so we'll do another iteration of the loop and have that picture. And now V is finally null, and we return W. And who believes that this actually reverses a list? Because that was a proof. All right? The ancient Egyptians had proofs by running an algorithm. They didn't know about quantifiers and logic, but they said, look, it works. And so there we go. All right, now let's describe this in separation logic. So let's first talk about heaplets in separation logic. X maps to 1 y star y maps to 2 null is described like this. And if we break apart that separating conjunction, we see that the left-hand conjunct characterizes that little heaplet with just one con cell in it. And the right-hand conjunct characterizes that heaplet with one con cell in it. And you notice that there's a dangling reference out of this heaplet. And that's perfectly okay. That's the way separation logic works. Okay. And then if we hide y behind a quantifier, as I've done on the bottom of this slide, you can see that we're beginning to sort of characterize a linked list that we have only the head of. And who knows where it leads after that, but it gets to null eventually. Okay? So now we can describe linked lists in separation logic, as I've done here in this line. And this is not so different from what Reynolds wrote down. P is a list terminating in null and representing the sequence sigma if, well, P equals 0, that is null. P is a null pointer, and emp. We need, so this and is not a star, it's an ordinary conjunction. These two different facts describe the state. Well, P equals 0 is a description of the local variable P. That has nothing to do with the memory to which separation applies. And emp says that the memory to which separation applies is empty. That is, the footprint we're describing here of that memory, the subset of it, is the empty domain. All right. Or there exists a y such that P is a pointer to a cell, a struct containing H in its first field and Y in its second field, separated from Y is a linked list representing sigma prime. Well, that's a recursive definition. Recursive definitions aren't really allowed in logic. But inductive definitions are allowed, and fixed points are allowed. So here's a fixed point. List rep is how you write that down in the syntax of Calc. If sigma is a list of vals, val is just the CompCert value type that could be an int or a float or a undef or a pointer or a long int or a single precision float. Okay, but if sigma is a list of vals, and P is a val, presumably a pointer value, and :empred means that a predicate in separation logic is a predicate on memories, right? So a memory predicate. You can think of memory predicate as just, memory with footprint arrow prop, but it isn't. It's like that, but with step indexing to achieve sort of higher order contravariant recursion. The user of Verifiable C doesn't need to know it's in an empred. This is a logic, and the user of the logic doesn't need to know the semantic model by which the logic is proved sound. Okay, either sigma is h cons sigma prime, or it's nil. And if it's h cons sigma prime, then there must exist some y so that data at, well, data at is just this maps to operator. And when Reynolds writes down that maps to operator, because he was a theoretician, he was not obliged to say which struct type in C we're actually talking about. But here I need to say it's this struct type that P is a pointer to. And therefore, the values of its fields, you know, I want to say are H and Y. Well, the number of elements of this tuple depends on which struct type in C I'm talking about. So this data at is actually a dependently typed predicate. And where does T struct list come from? The sort of syntactic description of a C language struct type in the abstract syntax tree. It comes from CompCerts having parsed something into C-lite ASTs. All right, star list rep sigma prime y. Well, sigma prime is structurally a substructure of this, so this is a nice fixed point. Or nil, in which case bang bang is to embed a prop into an empred. I think Adam had different notation for that. And emp. So there's linked lists in separation logic, and you can just write it down as a user. It doesn't have to be built into the system in any particular way. Yes? Oh, that's a permission share for access. Top means you have exclusive access to it. We can also have shared read, concurrent write in our concurrent programs, and I'm not much going to talk about that. Okay, so here is then the specification of the list reverse, that if in the precondition P is a list representing sigma, and you run this code, then the return value will be a list representing reverse of sigma. Oh, and by the way, whatever memory represented this has been destroyed, and it's been replaced with memory representing that. And we notice that it's actually in place. It's the same memory, and that's fine too. But yes?
If this had not actually destroyed it, how would we have distinguished that in the first condition?
Oh, well, then you'd have P, you'd have this star that, and you get both. Gotcha. Right. Okay. Right. So now we can write down the loop invariant. So we're sitting right here. We're about to do another iteration of the loop. We have this picture. W points to a linked list. V points to a linked list. So, and we started with a linked list P that represented sigma. So the loop invariant, written down by Reynolds in 2002, is that there exists a sigma 1 and a sigma 2, that sigma equals the reverse of sigma 1 concatenated with sigma 2, and W points to a linked list representing sigma 1, separated from V is a linked list representing sigma 2. And as we walk down the linked list, that loop invariant will continue to hold. Yes?
It's not the reverse of sigma 1?
Well, we reverse it here. So either we reverse it here or we reverse it here.
W shouldn't represent the reverse of sigma 1?
Well, the first element of sigma 1 is here, and the second element is here. Now that's either I put a reverse here or I put it here, but I don't think I should put it in both places. Okay. So let's translate those two things into calc. So on top, I have the specification of the reverse function. Underscore reverse is the C language identifier for a C language variable, the name of the reverse function. And as we know, the C compiler puts an underscore before its identifiers when it gets to the a.out. But anyway, names that start with an underscore are just identifiers, which is to say they're positive numbers that represent something in the symbol table. Pre is the precondition, and post is the postcondition. And the precondition is not just a formula in separation logic. It gets to be parameterized by the value of the function parameter. So there's where we get to mention that there's a function parameter, the C identifier underscore P, whose C language type is pointer to struct list. Now the precondition has each formula in our sort of lifted separation logic has three parts. One is pure propositions that are always true, and I'll show you that on the bottom half of the slide. So prop is just a list of propositions. Local is a list describing the values of your local and global variables. So we say here that the C language variable underscore P contains the coq value P. P is bound right here. So you can think of with as a for all quantifier that binds some coq variables over both the pre and the post condition. And then the sep clause is a semicolon separated list of conjuncts, of separating conjuncts. Here there's only one. It says P is the head pointer of a list representing the sequence called contents. And the post condition says there exists some P that's a value. I really shouldn't have used the same name here as here. This is just another coq variable. And coq doesn't mind if I put another variable in a hole of a scope of a first variable, but it sure makes it confusing for the human audience. Sorry about that. And the return temporary of this, so this is the special name for the thing you're returning, has the value P. And there's a list starting at that P that represents rev of contents. And rev is just the coq sequence reversal from the coq standard library. All right. Yes?
So is the ret val kind of for any expression in your language?
No, the ret val is in the post condition the return value of the function.
But I mean, could you have had an arbitrary expression instead of a function call in that form? Like at the top where you said ret val equals reverse. Could you just
This is a function spec. It's not a general judgment. Okay. And then the loop invariant. Here is what Reynolds would have written. So because, all right, let me step back to the original sin of Hoare logic. The original sin of Hoare logic is the pun that confuses program variables with logical variables. All right? So you get to use in your logic the same names for variables that you're using in the program. But what you really mean is the value of that program variable at this time. And when you're doing things on pencil and paper, you can get away with that. But to keep ourselves sane in a typed logic, it's not a bad idea to separate the concepts of a coq variable from a C variable. And so that's why we have this underscore P and that P that are different kinds of things. Because of that, we happen to need 4 existentials instead of 2. So CTS1 is just sigma 1, and CTS2 is just sigma 2. And here's a proposition that's true for all time, that contents equals the rev of CTS1 appended with CTS2. Well, for all time is a bit of an exaggeration, because these are bound variables bound right here, so within the scope of that binding. But that's a coq proposition. Oh, we'll use this loop invariant in a bigger coq proof that happens to have contents above the line. Well, we'll use it. I'll show you where we use this. And then the local variable W holds the coq value W. The local variable V holds the coq value V. There's a separating conjunction, so read this semicolon as a star, of list rep CTS1W and list rep CTS2V. Yes?
Dumb coq question here. So the top thing ends in a period, but it seems like the second thing is part of it
No, the second thing is not part of the first thing. The second thing is part of what's on the next slide.
Okay, but it is part of something, it's not.
It's part of something because it does have a free variable, as you see. So let's get there when we get there. All right, you may notice that certain parts of this notation are a little bit like what Adam showed, right? This pre and post and parameters. And indeed, you know, I read Adam's paper in 2013. I said, that looks like nice notation. There's his notation that he showed you 2 days ago, and it looks sort of similar. But sort of the basics of doing a separation logic for C, we started doing in 2006, and here's an early publication of a little baby separation logic for an actual high-level intermediate language of the CompCert C compiler. And our point was not only to make a separation logic for it, but to prove the soundness of that separation logic with respect to the operational semantics of CompCert. But CompCert had a big step operational semantics at that time, and I really wanted to do this with a small step operational semantics. So we convinced Xavier to change the semantics at the higher levels to small step, as he showed you. Okay, so now let's do the proof of this program. So let's start from the beginning. Line 1, import the verified software toolchain proof system. So that's just a Coq library. Line 2, import the abstract syntax tree, the C-Lite abstract syntax tree produced by the front end of Coq after it parsed this program. So this reverse.v that we're importing now is the output of a phase of Coq. 2 lines of boilerplate that are sort of identical in every such development that I won't tell you about. And then let's make an abbreviation for, hold on now. Okay, capital T, T-struct, that's a CompCert C abstract syntax constructor of a description of a C language type. And underscore list is the identifier that the user used in the source program, struct list. So this stands for struct list with no funny business. That's what no attributes means. Yes?
So part of the output of CompCert is inductive definitions that you import?
No.
It's not just data?
No, hold on. So the normal use of CompCert is you say ccomp, and it takes in a .c file and it produces a .s file. Okay. There's a different utility called clightgen, which just invokes the first couple of phases of CompCert to get to abstract syntax trees that happen to use this inductive constructor, tstruct, which the keyword struct is the same in every C program. This inductive constructor, tstruct, is the same in every C program. And it pretty prints it out as a .v file.
So the underlying list is not...
The underlying list is the name in Coq that CompCert chose for the identifier. So the type of underscore list is positive, that is ident. Okay, so that's just a convenient definition. And here's list rep that I showed you on the slide, exactly as I showed you on the slide. And let's tell Coq not to simplify that unless we explicitly unfold it. And then when you define a new mpred, it's convenient for you to prove sort of 2 standard lemmas about it. One is, from a list rep, what pure propositions can you learn? And so if P is a list rep, if P points to a list, then P is either a pointer or it's the integer 0. It is not some other integer, it's not a float, right? So that's one fact you can learn. And this right here is our notation built with the Coq notation feature for entailments in the mpred system. Oh, and you learn that P is equal to null val if and only if the sequence that's represented is the empty sequence. And Adam showed you some lemmas like that. And by So step one, what pure propositions can you learn just from a memory predicate? And then another thing you need to tell it is, what can you learn from the fact that P is a list rep, that it's allowed even to test P's value against null? Because you wouldn't think so, but there are some things you could put in a C variable that would be undefined to test against null. And so by putting this hint also in the valid pointer hint database, you give the proof automation some things that it can do. All right, but those two things when you define a new memory predicate. All right, here's the spec of the reverse function, just as I showed it to you on the slide. So then we'll gather, yes?
So you don't put the spec in the original C program?
Nope. The C program is the C program. If I want to prove something about OpenSSL's HMAC function, then I would like to prove it about OpenSSL's HMAC function, which doesn't happen to have these things embedded into it. But there's another reason I don't embed the specs into the program. And in particular, I'll show you when I remind me if I don't mention it when I get to the loop invariant. I'll show you another reason. Okay, so that's the spec. Now, let's combine all the specs that we've defined for all the various functions into a global spec gprog. So when I'm proving the function body of one function, that function might call other functions. And so it needs separation logic specifications for those other functions. And so if I combine together sort of a list of all the specifications of my functions, then I can pass that to my verifications of the bodies of each of the functions. And I can even put a recursive function, I put its specification into gprog, and then I get to use it while I'm proving the body of the recursive function, which sounds like circular reasoning, but it isn't. The logic permits this, and the logic is proved sound through the miracle of step indexing. Okay, so now we're ready to prove the body of the reverse function. Semac's body is the judgment for proving that a function satisfies its specification. It takes vprog that describes basically the types of all the external global variables in C, another dealie that John Reynolds didn't have to deal with. It takes gprog that describes all of the specifications of the global functions. It takes the function body of the reverse function, that's f underscore reverse. That comes from CompCert. It's an abstract syntax tree. And reverse spec is the last argument, and that's the thing we just defined. So we're going to prove that f reverse implements reverse spec. Okay, so that's our proof goal. And we use this tactic from the VST Floyd proof automation system. And what it does is it gives us a Hoare triple that we have to prove. Right? It's the Hoare triple of the function body with the precondition of the function and the postcondition of the function. So what's that look like? Well, Semax is the name of the Hoare judgment. Delta is the thing that contains all the global specifications of things, including the specifications of those global functions that we might call, and the types of the global variables, all sorts of useful information for this judgment. And then this is the precondition. And you might recognize it from the specification of our function. It says the C variable underscore P contains a value P, and in memory, P points to a data structure representing the sequence contents. So that's the precondition. Here's the command. Let's see. There's the command. S-sequence is CompCert's abstract syntax constructor for the semicolon, or for a sequence of commands. The first command is W gets 0. I bet you didn't know there's a cast in there, an implicit cast in the C language, and so by the time we get to C Lite, that cast is made explicit. And then there are some more commands. The more commands are abbreviated. Abbreviate is my definition that has an implicit parameter for all the good stuff. And so, there are some more commands there. Let's just get through this first command, and then we'll worry about the more commands. And then finally, here's the postcondition. And the postcondition is also an abbreviate because we're going to do forward proof in Hoare Logic. Now, usually in Hoare Logic, people did backward proof. You start from the postcondition and work backward through verification condition generation to the beginning of your block, and then you prove an entailment. That's backward proof. You can do forward proof. In separation logic, it's particularly attractive to do forward proof because as you do a load, you need to have proved that you have a conjunct that you can actually do a load from. So we're going to do forward symbolic execution of the program. And by symbolic execution, usually in symbolic execution, that means variables don't stand for like numbers, they stand for symbolic values, right? What's the symbolic values here? Well, the symbolic state is a judgment, an assertion in separation logic. So my symbolic state at the beginning of symbolic execution of this entire function body is right there. It's the precondition of the rest of the function. Okay, so if we're going to do forward symbolic execution, let's go forward. And the blue thing is a comment. We're going to go forward through W gets null. The proof automation can figure out that this is an assignment statement. It's right there in the judgment, set. And it knows what proof rule to use for an assignment statement, so it will apply that proof rule for you. And you should expect to see what? Well, here's the Hoare triple that we have to prove about the rest of the function body. It's got a precondition here, and a command, and a postcondition. And the precondition says W contains 0, and P contains P. So that's good. So you can think of the highlighted thing as the current assertion as we go forward in symbolic execution of the program. So let's go forward through V gets P, and you should expect to see in the current assertion after that V equals P. So there it is. Underscore V, the C variable, contains P, the value that happens to also be in the C variable underscore P. All right, now we get to the while loop. You can see that we've gotten to the while loop right here because we have a sequence of the while loop with some loop body that's abbreviated, followed by some more commands after the while loop. To do forward symbolic execution through a while loop, the user needs to supply a loop invariant. The proof automation does not figure out loop invariants all by itself. So here was the loop invariant. We use the tactic called forward while, and we need to supply a loop invariant, and there is the loop invariant. Notice that this loop invariant has a free variable contents. I don't need to order you to notice this because you guys have already noticed that. Where did contents get bound? Well, contents is there above the line, right here. So we're going to use this loop invariant in a scope where it happens that there are some things above the line, and we're free to use those things above the line. They're just calc values. But that also explains why it's inconvenient to write these annotations in the body of the function itself in the source code. Right? We're going to use these assertions in a place where we're already able to take advantage of the fact that we're in the proof assistant with some facts above the line. Okay, so I've already explained this loop invariant to you a couple of times, so I will just go through the forward while tactic. Bingo. Notice we have 4 proof goals now. And the proof goals are the stars here. Goal 1, the precondition implies the loop invariant. That's the kind of thing you always have to do in a Hoare logic proof, that we're going to use the rule of consequence to prove that whatever assertion we had gotten up to by now implies the loop invariant of this loop. We will also have to prove that the loop invariant is strong enough to imply that evaluating the expression in the loop test will not crash. That will be the second proof obligation. The third is that the loop body preserves the loop invariant. That's traditional in Hoare logic. And then forward after the loop, the rest of the function body is correct. So let's go into that first proof goal. We need to prove that the precondition implies the loop invariant. So that's an entailment in separation logic. It's not a Hoare triple. It's just this implies that. And here's the form of our entailment. let's see. Here's the left side of the entailment. It's just an assertion. Here's the right side of this entailment. It happens to be an existentially quantified assertion, right? And there's this global context delta, which characterizes some things about global variables and global specifications. And you can think of that as sort of part of the left-hand side, if you like. All right, so to prove this assertion, we need to exhibit some values for the existentials on the right-hand side. And we do that with the capital E exists tactic. So let's see. To prove that list rep contents P entails list rep CTS1W and list rep CTS2V, well, remember we're at the beginning of the loop. We haven't put anything into W yet. So CTS1 ought to be nil, which is our first demonstrated value. And CTS2 ought to be the whole sequence. So that's our second demonstrated value. And then we have to demonstrate values for W and V. But we know the current value of W, it's 0. So null val is just an abbreviation for vint of int.repr of 0. What does that mean? 0 is the mathematical integer 0 of type Z. Int.repr of 0 is the 32-bit signed or unsigned representation of that. So that has type int32.int. And vint injects that into the calc value type, saying, yes, it's an int, not a float or something else. All right, so that's null val. And then we need the exists v here, we need to provide a value for. Well, what is in underscore v? We happen to know that it's p, so let's say so right there. So that's 4 exists. So all the existentials have been instantiated now, and this is the entailment we have to prove. Well, we have a tactic called entailer bang that, tries to solve entailments, or at least solve the parts that it can and leave the rest for you. So let's apply entailer bang. So this is what we have to prove. All the rest, it figured out. Is this true? Well, yes, it's true. We can unfold list rep. And if you remember list rep, if the contents is nil, what does it tell you? It tells you that the pointer is a null val and emp, that there's no spatial part of this. And so we ask the entailer to try again on this simplified entailment, and it solves it. Okay. Second proof obligation from forward while is that the loop invariant implies that it's safe to execute the loop test and it won't crash. Well, what was the loop test? It's that V is not null. Is it safe to execute V is not null, or might that crash? Well, it might crash. If V is not initialized, then that's undefined behavior, and you're not supposed to do that. So it's not trivial that the loop test might crash. How do we know the loop test will not crash? Well, let's see. We know that the C variable V contains this value V, and we know that that value V is the head of some list rep, and the hint that we put about what propositional facts you can extract from a list rep is enough to prove that this is all going to work. So we call the entailer and say, can you prove this? And it can. Okay. Third, the loop body preserves the loop invariant. Okay, well, the first command in the loop body is, where was it? There it is. It's this. T gets V arrow tail. And so we need to dereference V. What do we know about V? Well, there's a list with V at the head. So that means either V is null or V is pointing at a const cell. And if V is null, we're in trouble, right? We can't safely dereference it. We happen to know V is not null. How do we know that? Well, it's up there above the line. Is pointer V. How did that get above the line? Well, when we entered the body of the while loop, the loop test must be true. That's a fundamental notion of Hoare logic, is that in proving the loop body, you get to know that the loop condition was true. And so that got automatically put above the line by analyzing the loop condition. Okay, so here's how we're going to unfold this list rep, which is just a fixed point. We can unfold it. So first we're going to, well, let's do this one step at a time. Let's do case analysis. Is CTS2 nil or not? So that's this. It's absurd for it to be nil. So let's handle the first case. We're going to unfold that list rep nil v that you can see over here. So unfold list rep at 2. It says v equal null. So this intros tactic brings things from the precondition, including propositional facts from the precondition, above the line. So watch, the v equals null val that's there in the precondition will now be above the line. It's h0. And, well, let's subs to v. So now in HRE we have is pointer null val, and that's a contradiction. Null is not a pointer. Okay, so the absurd case is handled, and now we have CTS2 is H cons R. So if we unfold that same list rep, this one right here, and then fold it back down again, we get that there exists a value y, that there's a struct at y, sorry, there's a struct at v pointing to hy, and there's a remainder of the list at y. Okay, and it's so there's an existential in the precondition of our Hoare logic judgment. That's sort of like, we know it exists, let's destruct that existential. So intros y will move that y above the line. Bingo, there's a value y that we can now use as an abstract value. Well, this data at right here that starts here and continues into the next line to here, the fact that v points to a struct with fields, values h and y, is enough to go forward through these two commands to fetch v arrow tail and to store v arrow tail. So let's use the forward symbolic execution built into the tactical automation system to go through these commands. Okay, we are now at the end of the loop body. And so now we have to prove the entailment that the assertion here at the end of the loop body implies the loop invariant. Well, how do you prove an entailment? You ask the proof automation system if it can prove the entailment. And it says, I can't prove the entailment, but I can simplify it down to this. Now, one thing that's simpler about this is there's no local variable bindings anymore. The left-hand side and the right-hand side of that entailment were in the same state. Whatever the value of underscore v was or whatever, it's the same in both sides, and we can just give a name to that. And so we have to prove this entailment that there exists this for tuple. That's sort of ugly. It has uncurried the existentials of the loop invariant. But in any case, we need to provide some for tuple x so that the first thing will sort of be the CTS2 of the next iteration. And that's the second thing, sorry, the second thing. The first thing will be the CTS1 of the next iteration. The second thing will be the CTS2 of the next iteration. The third thing will be the value of v in the next iteration. And the second thing will be the value of y in the next iteration. No, sorry, the value of w and the value of v. So anyway, we can provide these four values and ask the entailer if it can prove it now, which it can't. It leaves these two subgoals. If it leaves two subgoals, one is purely propositional and the other is pretty much purely spatial. What's the propositional subgoal? That the reverse of CTS1 concatenated with H cons R is equal to the reverse of H concatenated with CTS1 all concatenated with R. Okay, so if we simplify that, we'll be sort of evaluating that second reverse on H cons CTS1. So I'm going to simplify. So now that's reverse of CTS1 and then snock H onto the end. Okay, and now we can use the associativity of append. That was what I suggested to Adam. Remember when he said, what do we do now? Well, you use the associativity of append. I happen to know it because I'd been thinking about this. All right, so if we do that, you notice the right-hand side is now reassociated. And actually, this is just proved by reflexivity. Okay, so that was the propositional goal. Here's the spatial goal, that this sort of, the data structure description on the left implies the data structure description on the right. And the way we're going to prove this, how are we going to prove this? On the right, we have a list rep of a sequence H cons CTS1. So that's got to be a cons cell followed by the rest of the sequence that characterizes, that represents CTS1. So let's unfold that list rep. That's what this does. And when you unfold list rep, it says, okay, there exists a Y. We need to prove that indeed there exists a Y so that V points to the cell with H and Y. Up here, V points to the cell with H and W. So I suggest that we tell it W. That's our only hope anyway. So there, W. And now see if you can solve it, which it can. Okay, so we proved that the assertion at the end of the loop body satisfies the loop invariant. Yes?
I noticed that before, for the separating conjunction, we used semicolons. Here there were a bunch of...
In the notation called sep, we use semicolons to separate these elements of a kind of list. And when we're in a lowered separation logic expression that doesn't have prop local sep, why do we not have prop local sep? All the props have been moved above the line. All the locals, we're talking about the same state before and after, so we don't need the concept of local variables. And so we're just left with sep. And now we may want to reassociate. The semicolon notation doesn't permit reassociation there, and the star notation does. So that's why. Okay, we're done with the loop. And what we have in the assertion here, the prop local sep, is the loop invariant. That's the loop invariant, basically. And in Hoare logic, as you recall, we get to know that the loop condition is false. And where is that? That's at HRE right here. V equals null val. So that came from the analysis that the loop condition is false. Okay, and what do we have? We have a return statement, return W. So let's go forward, forward through return W. Now we're truly at the end. We need to prove that the return W satisfies the postcondition of the whole function. So, so that's this, that we have a list rep of contents 1 W separated from a list rep of contents 2 null val, and that has to entail somehow that there's a value x, that there exists a value x such that x equals W and the list rep of rev of CTS1 plus CTS2 star emp. Well, this is a mess, but I know what to guess for x. I have to provide any value that happens to be equal to W. That's easy. Let's try W. So let's do exists W, semicolon, and Taylor. So this is now what we have to prove. This looks like a lot what Adam had to prove, or what John Reynolds had to prove, right? Why is it true? Well, let's see. H1 right above the line says if null val, if and only if null val equals null val, then CTS2 equals nil. So let's rewrite by CTS2 equals nil in the stuff below the line. So CTS2 will be replaced by nil. Okay. And then if we unfold that second list rep nil null val and fold it back up, we get this. And it's sort of messy to have propositions in the left-hand side of an entailment when the entailer can just pull them above the line. It pulled it above the line, but in the process it noticed that it was sort of useless. Null val equals null val. That doesn't tell us much, so it cleared it out of the way. Okay, now this is what we have to prove. So, why is this true? Let me make it more readable. Well,
Rev is involutive.
rev is involutive, but we don't have rev of rev, actually. We have rev of app.
To get rid of the.
We have to get rid of the append nil. So let's rewrite by something that knows that something append nil is the same as something. And then let's rewrite by rev involutive. Now we got to prove this, which is trivially true by auto, and we're done. Okay, so that's how you prove list reverse in Verifiable C. I could show you how to prove the SHA-256 implementation from OpenSSL, but it would take longer. And I got a train to catch. So let's move on.
One question about that?
Yes?
So the specification there is that it is based the same as the SHA-256 implementation in the Lina, right?
Right. So the way we went about that verification, the SHA-256, is first we took the Federal Information Processing Standard 180-4, which is the description in math and English of what SHA-256 is doing, and we translated it into a pure functional program in Galena. And then we proved that the C program correctly implements the Galena function. All right. So that's the proof script I showed you. Let's talk about the principles of how do you specify C programs. So here's a little C program. It walks through an array, finding the smallest element and starting with the first element as its first guess about the smallest element. So it's a pretty simple program. And A is a specification of it that says, well, if in the precondition, the length of the list, length of the array, well, no, it's the length of the list. But you see, array A sigma says, at address A, there's an array that represents the list sigma. And that had better be a non-empty list because we're using the first element right here. So the array can't be empty. And the post condition says, and so notice there's a propositional part and a spatial part. And the post condition says that for every j that could be an index of that array, the return value is less than or equal to the jth element of sigma. All right, that's a perfectly good specification, although it's not as strong and precise a specification as you might want. It just specifies that that what you return is pretty small. If you want that what you return is actually also one of the things that was in the array to begin with, you'd want specification B, which says, oh, and by the way, let's see, there exists an I such that, the return value is sigma sub I, that the ith element of the list is the return value. All right. Now, specification C is another way to specify this list. It says, let's define a function in Galena that does something purely functionally on sequences, that is lists, not arrays, and then relate what the imperative program does to the functional program, saying this computes fold min, et cetera, on sigma. And that's a very precise specification. That sort of characterizes all of the sort of observable input-output behavior of that program. It is provably equivalent to specification B, okay? And And yet specification B looks shorter. And even in Calc, specification B is shorter. So isn't doing it this way unnecessary extra work? Because we haven't really proved that this characterizes the smallest element of the array. So that's the question. If we use specification C, what we're doing is we're proving that the C program implements some functional program, and then we've still got to do a proof about the properties of the functional program. Whereas we could directly use Hoare logic, separation logic, to prove the properties of the C program without this extra step in the middle. And the answer is, yes, you should do it this way whenever possible. And Zhang Xiao has been explaining the reasons to you that you want to prove once things in the horrible program logic of C, right? My horrible program logic is proved sound, by the way, okay? And then you have a functional program, and the proof theory of functional programs in Calc is much easier, so you can prove lots of properties about your functional spec. So consider this as a low-level functional spec that corresponds maybe reasonably closely to the C program in some ways. And you prove this once, then you can prove lots of properties, or harder, or just one property, but hard properties of the functional spec. Okay, and doing it this way allows you to take advantage of what I call modularity of expertise. So here's the Galena function. Here's the C program. Here is the refinement proof that I would do in Verifiable C, or Zhang would do in certified abstraction layers. Here's a properties proof of the kind you've been doing in Calc about, Galena functions. And when you build all of this, different people can work on different parts and not even understand the other parts. So, so let me come back to this picture. But aside from Zhang's reason, which is you do this proof once and then you can prove lots of properties, there's this other reason that the people that know about C programming don't have to know about Galena programming. And those people don't have to know about, well, this is just Haskell programming, really. And those people don't always have to know about the high-level properties in logic. And even the people that specify these high-level properties don't have to know how to do this proof. And the people that know how to do this proof might not know how to prove things about C programs or care to do it, and vice versa. So you can do engineering of verification with engineering teams with division of labor. All right, binary search trees. You've seen binary search trees before. I know you have. And here's binary search trees in C. Here's a program. The argument T of this insert is a pointer to your binary search tree. And the reason we need a pointer to this is imperative binary search trees with update in place, because, this is C programming. But even with update in place, if the original box was null, it was a leaf, right? It will be replaced by, the initial node. So we need this pointer to a pointer. And look, typedef struct tree is tree box is a pointer to a struct tree. And then we just have struct tree as an ordinary tree node. And so let's run this program. We want to insert I into the tree with F and B and L and E and R. So by the time we get to where the arrow is, X equals I, and P is the dereference of T. So that's the picture. Is everybody happy with this picture? Okay. If P equal null, well, yes.
If you put that into display mode, it'll be larger.
Oh, I'm not even in display mode, am I? Right. So let's see. P is not null. It points to a struct. So the if statement will go to its else clause. Let's go there. And it has done y gets P arrow key. Well, P arrow key is F. So y equals F. Now what? If x less than y, I is not less than F. So we'll go to the else clause. And the else clause says T gets the address of P arrow right. All right. This is a wonderful feature of the C programming language. Not found in any language invented before or since. Okay? You can take the address of about anything. And so what this does, it makes T point at that field of that struct. Okay. So now we're back up at the loop. And we did P gets star T. So now P points at that next node with an L in it. P is not null. So we go here. Y gets P arrow key, so Y is L. X is less than Y, so we go here. And T now points at ampersand P arrow left, so it points at the left field of that L node. And we're back up at the top of the loop. P gets star T. Now P is null. So this line right here, star P gets P, sorry it's not showing up very well, is going to assign, well, it's going to malloc P to point at this node, right? This node didn't exist yet. I drew it in the picture, but it really only gets created here by this malloc. We'll fill in the I into that guy and initialize the left and right to null and make this red box point to it. So there we go. Okay, and now we're at the return, and we're done. So who believes this program works? You better believe it. I just proved it to you in the sort of ancient Egyptian way by running it on one input, or the modern software engineering way, right? Okay, so let's prove it in separation logic. So here's trees in separation logic, and it's just like lists. If you read this, you'll see that, either the tree is a leaf or it's a node. And if it's a node, now there exists two pointer values because there's two children, and the separating conjunction has a data at here and two other separating conjuncts for the subtrees. This tree rep APA represents the subtree. Okay, and we can do the same of the separation logic description of that tree box, the one little box that has a pointer to a tree in it. And here's the specification of the insert function, which says, if you start with a tree box at address B containing the value T, then, representing the tree T, sorry, then in the end you'll have a different tree box, still at B, but representing something else. And what are these? I'm referring to this capital E and this capital T and this insert function in Galena. And where did they come from? Well, they came from verified functional algorithms. That is, the functional program that you verified. Who verified that in the homework? Good. That was a pure functional program. You didn't think of that as an imperative program, but it's the specification of an imperative program. This highly imperative program that takes the addresses of fields and does all that crazy stuff is specified by this Galena function that's just plain old insertion in search trees. And so if we go back here, we see that it's very typical that, you refer to this pointer B represents this sort of Galena object. We already did that for list reverse. It's just that the Galena object was just type list and the rev function, and you think of that as, oh, that's just math. That's sort of built into Coq. But it's not built into Coq, it's functional programming in Coq. Here it's a little more obvious because you got to see the functional program. Okay, so here we are, having stepped a couple of steps down the loop, and we're in this situation where T points at that field, and the contents of that field is some subtree. Now, how do we describe this in separation logic? Right? That we have a root pointer that describes a tree, but a whole tree, right? All the way down to its leaves. We want to describe the part of the tree down to some hole, and the rest of the tree from that hole down to its leaves. And here we go back to Reynolds. Reynolds said, separating conjunction that asserts that its subformulas hold for disjoint parts of the heap, and a closely related separating implication. And the separating implication in separation logic is written with a sort of dash star symbol that looks like a magic wand. So it's called magic wand. So this formula right here describes the whole tree, all these parts put together with this thing sitting right in there. Okay, tree box rep. Tau 0 is the Coq tree, the thing of type, tree. And T0 is a val, it's a pointer value pointing at some place in memory. And this assertion says that at memory at address T0, there is some data structure that represents tau 0. And that was fine for the precondition of the function, but as we walk down the loop, that's not what we want to say. What we want to say is this. This is the magic wand. It says, well, there's something, this circle, that would be a tree box rep tau 0 T0 if you filled in some more memory next to it that satisfies, this, that is a address T representing tau. So that magic wand expression on the first line represents that data structure with a hole in it. And then the ordinary conjunct on the second line represents what you're filling the hole in with. Okay, so that could just about work for our loop invariant, but here's another thing you can say, that this data structure would be a tree no matter what tree you fill the hole in with. And that's good to know because we're going to update down there on the right somewhere, and we're going to be, by the time we finish, there will be a different tree in there. And it would not be useful to know that, oh, if you leave the tree alone, it would be the right tree. We need to know that for any tau prime and t prime, if you had a tree representation and you attached that, in memory separated from this, then you'd have a proper tree. And separate that from what we have now, which is not the same as what we will have in the future. So this right here is the loop invariant of that very imperative while loop that's the insert function. Yes?
I'm a bit confused that we can all quantify the T prime. Doesn't it say that as long as there's some position somewhere in memory where there happens to be a tree, I'm a tree? I would expect the T to be the same.
No, it doesn't say I'm a tree. I'm saying I would be a tree if you added this memory to me. If you could construct some memory in the future and then add that to my memory, then that thing would be a tree. Not that I'm a tree right now. I am this, yes?
But it doesn't say if you construct a tree somewhere at T prime.
Well, tree box, what do I want to say? Yeah, this really works. You're describing what you're going to fill the hole in with.
Will I have to specify where that hole is?
I have a hole somewhere, and if you fill it in, I'll be a tree. This is the loop invariant. Really works. Okay, yes?
In the middle statement, what does the star imply? Does it say that there is a separation between the space of the tree box rep tau t and tree box rep tau 0 t?
Yeah, the memory that this characterizes is disjoint from the memory that this characterizes, and together they make the whole heap that this statement characterizes. And you can see that they're disjoint. That's why I drew this picture.
I guess the confusion stems from the fact that tree box rep tau t is in both sides.
Well, it's on the left hand of this one. So this is sort of a negative position. If you fill this one in, for example, with that, then you'd get this. It's an implication. Separating implication is really hard to think about. It took me a long time to understand how to think about it until my student explained to me how to think about it. And the general theory of magic wand is sort of hard. So we've developed a discipline for the use of magic wand for filling in holes in traversals of data structures that once you get the hang of that, you use it in that discipline, and it's not hard. Okay. So let's talk about modularity of expertise for the the search trees. All right? The software engineer writes this C program with pointers to pointers. And I know how to write that C program pretty much correctly most of the time without knowing any separation logic. I knew that 30 years ago. All right. I used to not recommend to the sophomores to program with pointers to pointers because, taking the address of a field, doing that trick, it's a cool trick. It's in some ways a nicer program, but it's harder to get right, and I don't recommend it to people that are not going to verify their programs in Verifiable C. But if you are, then it's okay. Now look, the application domain logician can prove things about the purely functional search tree without knowing how to prove things about C programs. Raise your hand if you are exactly in that position, because you did it yesterday, right? And then writing the functional program doesn't require knowing how to do these proofs, because I could write that functional program 20 years ago. And so could most of you write that program before you came to this summer school, perhaps. The high-level property, well, we knew what the high-level property is for lookup tables, right? That, you can insert things in the table and look them up, and you'll get the same thing back again. So that has nothing to do with... so therefore, so there really is this separability of expertise that leads to engineering teams, that can work. And they don't even have to be on the same team. When I verified OpenSSL's SHA-256, the software engineer that wrote the C code would be very surprised to learn that he's on my team. Okay? It's modular. Now, that guy, when you prove, my proof that I didn't show you the proof, I just show you the loop invariant. But an interesting thing about the proof of correctness of the C program is that you don't need to know anything about the properties of search trees. You don't need to know that the thing on the left, is less than the thing in the middle. You just need to know that the C program is faithfully implementing the Galena program. And why the Galena program happens to work is not always relevant. So that's also a useful modularity of expertise. When I'm proving things about crypto algorithms, and I prove that the C program implements the functional spec, I don't really want to have to understand why crypto works. This is good. All right, so there's that, and I'm just about done, right? Verifiable C is a higher order impredicative concurrent separation logic. I didn't show you the underlined parts, higher order impredicative concurrent. So let me talk about them briefly. Concurrent means you have a shared memory parallel program written in C that uses locks or uses the C11 atomics. So it has lots of accesses to ordinary data, using ordinary non-atomic loads and stores of C, and it has some atomic accesses in, release acquire mode. And you can use concurrent separation logic very beautifully to reason about programs like that for reasons that are beyond the scope of this lecture, but those concurrency features are there. Higher order, well, you have your functional programs are higher order. They have functions that you can pass functions to other functions and return functions as results. You can do that in C too. And the functions you pass in C are traditionally thought of as a little weaker because they don't have free variables. You can't sort of make new functions at runtime by being in the scope of something else. But that's all right. The C programmers have an answer for that. It's basically called closures or objects. You package a function pointer with some data in a struct and pass that, right? Now you've got C++. All right? Well, C programs often have, if they're not C++ programs, you may have C programs with a kind of roll your own object protocol with lots of casts and void stars. And the program is still correct, even if it has casts and void stars. And we can prove that it's correct, but that requires quantification over predicates. And what is impredicative? Well, in this abstract data type, I'm hiding the representation. So I have an existential quantification over the predicate that describes the representation invariant, and the client doesn't get to see it. Okay. The client is implementing another abstract data type. So it's going to quantify over the representation to hide his own representation from the next client. Well, now I'm quantifying over a predicate that was built by quantifying over predicates. And in logic, that's sort of tricky. you may need to stratify things, otherwise it's unsound. But that would be no fun. We want a logic that can do that in a sound way. So we invented one, and we proved it sound in a different project 15 years ago with step indexing. All right, so Verifiable C, therefore, is a very expressive logic that can reason about lots of the things you actually do in C programs, pretty much all of them, I would hope. And not just pointer separation, but all the other fancy things you do with pointers and modularity and so on. And it comes with a proof automation system that I demonstrated a little bit of for you that helps you apply the program logic to the program. Okay, and you can read more about this in the reference manual for Verifiable C, which you can find in the distribution that's at that website. Although pulling the trunk from, the master from the GitHub repo is always a good way to keep up to date. And since we use Travis continuous integration these days, the master actually works pretty much all the time. And it's just our branches that are broken. Okay, so in conclusion, verified functional algorithms plus higher order impredicative concurrent separation logic is a way to do machine-checked proofs of deep functional correctness specifications of C programs. Thank you. And I'm sorry I can't take questions because I got to rush out the door and catch a train.
Will your slides be up in the
Eventually, I guess.
Thank you.
We've come to the end. I'm going to let you go soon, but we have a few people to